Let's paint a scenario.
You're feeling like eating a snack, and you try to open a bag of chips by pulling at the edges repeatedly. Once you're able to get a tiny opening in the bag, you find it very easy to tear the rest of the bag open, revealing the salty goodness inside.
But why does this happen? Why does the bag become easier to open when you make the initial tear? Let's dive into the intriguing world of material failure. Material failure often starts with deformation.
When you apply stress, which is the force acting over a cross-sectional area, onto an object, the material will have a reversible strain, which is the temporary change in shape and length of the object.
For example, this rubber band.
Below a certain stress level, it stretches proportionally, then snaps back to its original length when the stress is removed. This is elastic deformation. However, if you apply a high enough stress, called the yield stress, which is different for different materials, the material will permanently deform and will not return to its original length. This is called plastic deformation. For example, using a high enough stress to bend this paperclip leaves it stuck in a new shape.
Now how materials fail and break, or in the case of the bag of chips, rip wide open. Materials under cyclic or repeated stresses, which basically means that stress is applied, then is stopped or reduced, and then started back up again and keeps on repeating like this, can fail through a process called fatigue. This process is split into 3 stages: crack initiation, crack propagation, and structural failure.
The first stage, crack initiation, is when the first crack is formed in the material due to external stress. Crack propagation, which is the next and usually the longest stage, is where the crack grows steadily as there are more and more load cycles. And then, snap. The material undergoes structural failure, which is when the crack has propagated throughout the whole material and causes it to break completely. Stress applied to the material is highly concentrated at the tip of the crack, making it the weakest point in the material, thus driving crack growth as it is more susceptible to applied stresses. In materials with high plastic deformation, such as metals, the material around the crack can absorb the energy brought about by the stress applied by plastically deforming instead of letting the crack grow. This slows the propagation of the crack. However, brittle, meaning easily broken materials like glass, have minimal plastic deformation, so the stress applied propagates the crack more, eventually leading to a quicker failure. This explains why it takes quite a lot of stress cycles for your paperclip to break, while attempting to bend a thin piece of glass just a few times can break it.
Understanding these principles helps engineers design and build materials and structures that can handle stress without failing prematurely.
From plastic chip bags to bridges to aircraft, knowing how materials behave under stress is critical to making them usable, safer, and more durable. So next time you want to open a bag of chips, think of all the science at play. A little stress can go a long way.